Section 6.6, Calorimetry, Measuring Energy Changes. Calorimetry is the study of heat transfers by measuring the temperature changes in substances involved. When a piece of hot metal is placed in cold water, the metal cools and the water warms. The amount of heat lost by the metal is equal to the heat gained by the water, assuming no heat transfer to the surroundings. And we can go ahead and operate under that assumption there, no heat transfer with the surroundings. So what we can do is set up, well, using our equation Q equals mc delta T, we can set up the following. Q is equal to 0, which is equal to mc delta T for water plus mc delta T for the metal. Now here's an exact practice problem, or a good practice problem to work with. We have a 25 gram sample of a metal at 87.7 degrees Celsius. It's placed in 37.4 grams of water at 10 degrees Celsius. Okay, so think about this. We've got hot metal, cold water. What's going to happen? Well, the temperature of the metal is going to go down, the temperature of the water is going to go up, and it's going to stabilize. Now, the final temperature of the system is 15.4 degrees Celsius. What we need to do is calculate the specific heat of that metal. Now, we've got a table here that shows us a number of different metals. Aluminum with a specific heat of 0.892, chromium 0.45, cobalt 0.46, copper is 0.385, gold is 0.129, and iron is 0.442. Okay, I'm going to go ahead and write these out. So 0.129 and 0.442. Okay, now which metal is it? So the way that we need to set this up is we need to go with, well, 0 is equal to Q of our water times C of our water delta T of our water plus Q of the metal. I'm just going to write MET, C of the metal, and delta T of our metal. Okay, so we know a couple of different things. We know the C of our water, that's 4.184 joules per gram degree Celsius. We know that the temperature of our water, well, what happened to it? The temperature of our water, what we want to do is look at our final, which is 15.4 degrees Celsius, minus our initial temperature of our water, which is 10.3 degrees Celsius. Okay, so final minus initial is going to be our temperature change of our water. Now, Q of our water, that is something we don't necessarily, M. We need to change that. We need M, the mass of our water. We know the mass of our water. The mass of our water was 37.4 grams. 37.4 grams. Okay, so we have everything that we need to consider the heat change of the water. Now, the mass of our metal, or the M of our metal, well, that's 25 grams. The C of our metal, that remains unknown. I'm just going to write as CMET. That's what we're solving for. The delta T of our metal, well, we've got to do final minus initial. Our final is 15.4. Our initial is 87.7. Okay. All of this is going to equal 0. So the first thing that I want to do is I want to go ahead and do whatever math that I can. So I'm going to say 37.4 times 4.184, and then times our temperature change, which is 5.1 degrees Celsius. Okay. Now, what I also want to do is go ahead and, well, set these equal to one another. But the way that I'm going to do that is I'm going to take this whole chunk, everything that pertains to my metal, and subtract that. So now what I'm doing is moving this over here, negative. I'm going to say just metal stuff. And then I'm going to say negative 25 times C of our metal times, now is our temperature change. We've got our final temperature, which is 15.4 minus 87.7. That's going to be negative 72.3. Okay. That is equal to, and now I'm going to take this whole function right here and figure out a number for that. 37.4 times 4.184 times 5.1 equals 798.1. So I'm going to now be in a position where I can divide this 25 times negative 72.3 2.3, and whenever I do that, I'll be left with, well, this negative remains right here, so negative C of our metal is equal to 798.1 divided by parentheses 25 times negative 72.3 and close parentheses equals negative 0.44 or 0.442. Okay, now is that a problem? It really isn't. It's a negative value, but heck, two negatives, they're going to cancel one another out. So I'm going to erase that, erase that. So the heat capacity of my metal is 0.442. And lo and behold, there's the heat capacity for metal. Or for iron, I'm sorry. So what we have here is one thing cools down while the other heats up. And it seemed like, well, that metal, that dropped 72 degrees. The water only went up 5 degrees. Why is that? Well, if you compare the specific heat capacities, well, water, it took a lot of energy. It took a lot of energy going from that metal to that water to get it to change 5 degrees. Water has a very high heat capacity, which is kind of illustrated here. I hope this helps. We're going to go ahead and do some more practice problems related to this same topic in the next video. Well, thank you very much for watching. You got this.